My dear students, now we start with stereochemistry, an interesting topic in organic chemistry. Stereochemistry is something connected with the three-dimensional representation of a molecule. When we consider a molecule, we know the atoms are bonded with other atoms through chemical bonds. In organic chemistry, we know many of these bonds are basically covalent bonds. So, stereochemistry deals with the three-dimensional representation of the molecule in space. From one-dimensional and two-dimensional, I am seeing the molecule in a three-dimensional pattern, and this reflects stereochemistry of that particular molecule or compound. And the importance of stereochemistry is that in our biological systems, many reactions are directed by the stereochemistry of the molecule. For example, some drugs may be active only if we use a particular stereoisomer. Other stereoisomer of the same drug may be inactive or even could be toxic. And the branch of chemistry that deals with the three-dimensional structure of molecule and their effect on physical and chemical properties is called stereochemistry. And we give emphasis to organic molecule so that to represent a three-dimensional object, we should have an sp3 hybridized orbital. That means the shape should be tetrahedral. That is the concept we are taking in case of organic molecules. Moving to the details, we have to think about projection formulas. A projection formula is a representation of a three-dimensional molecule to a two-dimension to identify and understand the position of the atoms around the central atom. That means it is a formal two-dimensional representation of a three-dimensional molecule, and it represents the plane of the molecule with or without the designation of the position of relevant atoms by chemical symbols. When we consider a three-dimensional molecule to a two-dimensional picture or representing in a paper, we have to overcome many problems associated with these representations. So, configuration of a chiral molecule from three-dimensional picture to two-dimensional picture is called a projection formula. Basically, we deal with four projection formulas. They are Fischer projection formula, Newman projection formula, Soh's projection formula, and Flying-Wedge formula. There is another one, zigzag type formula is there, but we are giving importance to these four types of projection formulas. Now we see the first one, that is the Fischer projection formula. When we represent a Fischer projection formula, we easily represent it by a vertical and a horizontal line. So to represent a Fischer projection formula, we have to consider these things. So the carbon chain is projected vertically here. So the vertical line represents the carbon chain. And when we represent the carbon chain, the most oxidized carbon atom should be placed at the top or the first position. Now, the chiral carbon atom lies in the plane of the paper, and we will not represent the carbon atom here. We know a chiral carbon atom should be there for any molecule to show stereochemistry. So the chiral carbon atom will be there, but we will not represent it or show it as such. Then the intersection of the vertical and horizontal lines, that this particular point represents the asymmetric carbon atom. So in Fischer projection formula, we represent it by vertical and horizontal lines, and the intersection of the vertical and horizontal line assumes the presence of the asymmetric carbon atom. When we consider the horizontal bond, that is this particular bond, we say this is above the plane of the paper, or this bond is projecting towards the observer. That is, the horizontal line depicts or represents that this is or the constituents or atoms present at the horizontal lines are pointing towards the observer. The vertical bonds attach the carbon atom, asymmetric carbon atom, to be below the plane of the paper, or it will be away from the observer. So when we write the projection formula of any molecule, these factors has to be considered. See here another example. I am showing the projection formula of a particular molecule here. So I have a vertical line and a horizontal line, and that intersection represent the asymmetric carbon atom, and the horizontal lines shows that or denotes that this H and OH is pointing towards the viewer, or it could be represented as a structure here, while the vertical line shows that the COH and CH2OH is away from the viewer. So this is the projection formula. Now we move to Newman projection formula, which is very simple. When we consider Newman projection formula, we will consider a circle as the carbon atom, and the circle of the carbon atom represents it is the back carbon atom or rear carbon atom, and the first carbon atom is represented by a particular lines, 3 lines. Then the fourth bond is the bond between the second carbon atom. So the rear carbon atom is represented by a circle, and the lines projecting from the rear carbon atom, that is a circle, shows the position of the bond or substituents or groups. So in Newman projection formula, we represent two circles, and these circles will show you or consider as the carbon atoms on front and on back. And the front carbon atom, the bonds are represented by the lines originating from the nucleus or center of the circle, while the bond of the second carbon atom is represented by originating from the circle, that is the circumference of this circle. So this is the Newman projection formula. Newman projection formula is usually used for representing the conformations of molecules. And to identify and to understand the conformations, we usually use Newman projection formula. See here, this is the Newman projection formula of staggered and eclipsed form of normal butane. So in the staggered position, we could say the bond between the first carbon atom and the second carbon atoms are far apart. While in eclipsed, the bond of the first carbon atom and the second carbon atom is on the same plane. And these conformations are easily or freely rotate about the carbon-carbon single bond. So in Newman projection formula, we represent it by circles, and the bonds are represented by originating from the nucleus or center of the circle as well as from the circumference of the circle. So this is Soho's projection formula. In Soho's projection formula, we represent the carbon atoms or the bond between the two carbon atoms as a longer diagonal line. The down or the first carbon atom, which is represents the lower or the down portion of the diagonal line, and the second carbon atom is presented at the upper or higher portion of the diagonal line. And the bonds are represented at the edge of the lines. That means at the starting and ending of the line. And if we consider normal butane, this bond is represented between second and the third carbon atom. If it is a staggered configuration, the bond of the first carbon atom with the CH3 group is placed between the bond of hydrogen atom of the third carbon atom. But in eclipsed, it is placed exactly on the back of the CH3 group. That means the bond on the first carbon atom and the bonds on the second carbon atoms are on the same plane for eclipsed conformation of a Soho's projection formula. While for staggered conformation, the projection formula, the bonds is between the bonds. Now we move to Flying-Wedge or Wedge-Dash projection formula. The Flying-Wedge projection is the most common three-dimensional representation of organic molecules. So from the three-dimensional picture to a two-dimensional picture, usually we use Flying-Wedge projection formulas. In Flying-Wedge projection formula, the molecule is represented as dotted lines and a solid wedge. See here, solid wedge and certain black lines. This solid wedge represents the bond is above the plane of the paper, or we could say in this picture, if we are representing this C wedge H bond, that means it is above the plane of the paper, and the dotted lines or the broken lines represent it is below the plane of the paper. We know methane molecule is a tetrahedral structure. When we look into the methane molecule structure, this broken line carbon hydrogen bond clearly indicates that that bond is back to the plane of the paper, while the solid wedge formula clearly shows this carbon hydrogen bond is above the plane of the paper, or it is projecting towards us. So in Flying-Wedge formula, we use solid wedge and broken lines apart from dark black lines to represent the molecule from a three-dimensional picture to a two-dimensional picture. See here, we are representing the lactic acid using Flying-Wedge formula. These two are the enantiomeric form. One is L-lactic acid and another is D-lactic acid. See here, this OH representation, it shows it is projecting towards the viewer or above the plane of the paper, while this dotted lines is projecting away from you. See here, away from you. It is a tetrahedral structure. So its mirror image is the other enantiomer. So we could represent a molecule basically in a three-dimensional manner in a two-dimensional paper using Flying-Wedge formula. You got it? So Flying-Wedge formula could be more useful to represent a molecule in a paper as a three-dimensional representation. Now we move to the next topic, that is conformational isomerism. We know in organic compounds, especially in saturated organic compounds, there are carbon-carbon single bonds. At room temperature, these carbon-carbon single bond could be rotated. As a result, due to the rotation of carbon-carbon single bond, various spatial arrangements are possible for a saturated organic molecule. Without breaking the carbon-carbon single bond, they are spatially oriented at different directions. And this type of isomerism is called conformational isomerism. That means conformations or conformational isomerism is the process or phenomenon by which a saturated organic molecule orient in three-dimensional space in various different spatial arrangements due to the rotation of carbon-carbon single bond. So, conformational isomerism, the reason is the rotation around carbon-carbon single bond. And these isomers can be readily interconverted at normal conditions. And there are two types of conformational isomerism. One, conformational isomerism resulting from the rotation about a single bond, and another type is the conformational isomerism arising from amine inversion. We have to think about only the conformational isomerism or conformations resulting from the rotation of carbon-carbon single bond. Now we move to the conformations of ethane. We know ethane molecule is C2H6. So it could be represented like this. This is the first carbon atom and this is the second carbon atom. Each carbon atom is having 3 hydrogen atom. And there is a carbon-carbon single bond here. And this carbon-carbon bond could easily undergo rotation. If we see or observe ethane molecule from the front view or end view, the molecule could be represented like this one, because the first carbon mask or cover the second carbon atom, so that we could see only the first carbon atom, while all the 6 carbon atoms could be seen. Now see here, this rotation of carbon single bond rotation is possible, so that around this carbon-carbon single bond, a large number of spatial arrangements are possible. Now see here, if I take this representation, I can rotate this carbon-carbon single bond. Now see here, this hydrogen atom is presented between these 2 hydrogen atoms. See another one. Here, this hydrogen atom is exactly presented front of the hydrogen atom. That means I can rotate this carbon-carbon single bond, so that the position of this hydrogen atom, these 3 hydrogen atoms, changes relatively to this one. If I keep this carbon and hydrogen as constant, and if I am rotating this carbon and hydrogen, these hydrogen could be placed between these hydrogen atoms and along in a particular plane of hydrogen atom. That means for ethane molecule, infinite number of conformations are possible. Infinite number of conformations are possible because around this 360-degree, this carbon-carbon rotation occurs. As a result, this hydrogen atom could be placed at infinite angles comparing to the hydrogen atom of the back carbon atom. When we arrange these are conformations or conformational isomerism. And among these 2 extreme conformers are there. For ethane molecule, extreme 2 conformers are there. One in which the first carbon atom and second carbon atom having all the hydrogen atoms on the same plane. All the hydrogen atoms are on the same plane. See here, in this case, this is the hydrogen atom of second carbon atom, and this is the hydrogen atom of first carbon atom, and it is placed between the 2 hydrogen atoms of the back carbon atom. But see here, in this case, the first and second carbon atoms having the same hydrogen atoms on the same plane. So, ethane could exist in 2 extreme conformations. So, The conformations of ethane could be represented as extreme case as eclipsed conformation and staggered conformation. See here, in eclipsed conformation, the carbon atoms and the 3 hydrogen atoms are eclipsed each other. That means when we are looking from the front side of this eclipsed conformation, we could only see the first carbon atom and the 3 hydrogen atoms. That means the 3 hydrogen atoms of the first carbon atom and the 3 hydrogen atoms of the second carbon atoms lies in the same plane. See here, like this. That means we cannot see the hydrogen atoms of the second carbon atom in eclipsed conformation. Moving to the second extreme, that is the staggered conformation. In staggered conformation, the hydrogen atoms of the first carbon atoms are placed exactly in between the hydrogen atoms of second carbon atom. See here, it could be represented like this. See, this is the first carbon atom with the 3 hydrogen atoms, and these are the 3 hydrogen atoms of the second carbon atom. That means the second hydrogen atoms or the hydrogen atoms of the second carbon atoms are placed exactly between the hydrogen atoms of first carbon atom. Hence, we could say ethane could exist infinite number of conformations, but only 2 extreme conformations are possible. They are eclipsed conformation and staggered conformation. In eclipsed conformation, the hydrogen atoms of the 2 carbon atoms are placed one below the another, or the 3 hydrogen atoms of each carbon atoms are lying in one plane. While in staggered conformation, the hydrogen atoms of the first carbon atoms are placed exactly between the hydrogen atoms of second carbon atom. Now see here, this is the staggered conformation and this is the eclipsed conformation. When I am writing the Soh's projection formula, this is the Soh's projection formula of staggered conformation. See here, this hydrogen atom and the other hydrogen atom on the opposite direction. Moving to the Newman projection formula of staggered conformation. See here, this is the first carbon atom and these 3 are the hydrogen atoms of first carbon atom. And in staggered, the hydrogen atoms of second are placed exactly between the 2 hydrogen atom of first carbon atom. And this is the ball and stick model. Similarly, this is the projection formulas of eclipsed conformation. When we consider conformation, we have to think about a term called dihedral angle theta. Dihedral angle theta. And this angle is the angle created by 2 intersecting planes. See, for an eclipsed conformation, the dihedral angle is theta is equal to 0 because the hydrogen atom of first carbon atom and the hydrogen atom of the second carbon atoms are in a single plane. So the intersecting plane is same. So dihedral angle theta is equal to 0. So I am taking this carbon atom and this first hydrogen atom and this first hydrogen atom. So comparing these two first hydrogen atoms for an eclipsed conformation, the dihedral angle is 0. But when I am rotating the first carbon atom and it moves to a staggered configuration, staggered conformation. At the staggered conformation, the hydrogen atom of the first carbon atom is placed exactly between the hydrogen atoms of second carbon atom. That means there the intersecting planes create an angle of 60 degree. 60 degree. So for this first staggered conformation, the dihedral angle is theta is equal to 60 degree. So for any conformation, we have to think about the dihedral angle. That is the angle created by two intersecting planes when carbon-carbon single bond rotation occurs. Now see here, I have the different conformations of ethane here. See, I am taking the first conformation here. This is an eclipsed conformation. So I label the hydrogen atoms with same color here. So this first hydrogen atom of first carbon atom and this is the first hydrogen atom of second carbon atom. And they lies in the same plane. Hence the dihedral angle is 0. 0. But when I slowly rotate the carbon-carbon single bond, it moves to an extreme case called staggered conformation. In that staggered conformation, the first hydrogen atom of the first carbon atom and the first hydrogen atom of the second carbon atom creates a dihedral angle of 60 degree. So the rotation is again possible so that it moves to another eclipsed conformation. In this eclipsed conformation, the hydrogen atom of first carbon atom and the hydrogen atom of the second carbon atoms are in the same plane. Again the rotation occurs, it moves to another staggered conformation where the dihedral angle is 180. Why here the dihedral angle is 180? Because the angle between the first hydrogen atom of first carbon atom and the first hydrogen atom of second carbon atoms are exactly at opposite to each other. That is why here the bond angle becomes 180 degree. Again it converts and to eclipsed form, then staggered form, finally to eclipsed form. And see, this is the potential energy. And from this curve or graph, it is clear that the potential energy of all eclipsed conformations are high compared to the potential energy of staggered conformation. That means for ethane molecule, staggered conformation is more stable than eclipsed conformation. So we could say eclipsed conformations are least stable while staggered conformations are highly stable. So the energy diagram clearly shows that the potential energy of all the staggered conformation, whether the dihedral angle is 60 or 180 or 300 etc. The energy is minimum for staggered configuration, while eclipsed conformation the energy is maximum. Now see here, the barrier to rotation between the conformation is very small. That means in room temperature, the carbon-carbon rotation occurs. the energy is only 12 kilojoule per mole. 12 kilojoule per mole. That means the conformations occurs rapidly from staggered to eclipsed and eclipsed to staggered. The most stable conformation of ethane is staggered because in staggered conformation all the hydrogen atoms are placed at maximum distance. Hence, the repulsion is minimum. The repulsion between the hydrogen atoms is minimum in the case of staggered conformation because the distance between the hydrogen atoms is maximum. While in eclipsed conformation, the first hydrogen atom and second hydrogen atom is eclipsed. That means distance is minimum. Hence, eclipsed conformation is least stable and it is having high torsional strain. High torsional strain. So, for ethane molecule, the staggered conformation is highly stable while the eclipsed conformation is least stable. See, the stability of any conformation is affected by three factors. They are angle strain, torsional strain and steric strain. The angle strain is the strain induced in a molecule when the bond angles are different from tetrahedral bond angle. We know majority of the saturated hydrocarbons are tetrahedral in shape. Hence, their bond angle should be 109 degree 28 minutes. If there is any change in the bond angle, it causes a strain to the molecule and that strain is called the angle strain. The second strain is the torsional strain. It is the strain caused by the repulsion between the bonding electrons of one substituent to the nearby substituent. And another strain is the steric strain. So, this torsional strain and steric strain, these two strains are the reason why staggered conformation is more stable than eclipsed conformation. The torsional strain and steric strain is minimum in the case of staggered conformation and it is maximum in case of eclipsed conformation. That is why staggered configuration is highly stable, conformation is highly stable than eclipsed conformation. So, thank you my dear students. You prepare the notes and if you need the notes in a descriptive manner, you can contact me. But better, I feel you prepare the notes by yourself so that you may get doubts and it could be clear in the next class. Thank you. Thank you very much.